The speed of light is 299,792,458 meters per second. This is not an approximation. It is not a measurement with experimental uncertainty. It is a definition. In 1983, the International Bureau of Weights and Measures redefined the meter in terms of the speed of light. The meter is defined as the distance light travels in 299,792,458 of a second. The speed of light is therefore exactly 299,792,458 meters per second by definition, and the meter is whatever length makes that true. The speed of light is the most precisely known physical constant. It is not uncertain. Its value is fixed. The question is why it has this value rather than any other. And the answer, the honest, current scientific answer, is that we do not know. The speed of light appears in physics as a fundamental constant, a parameter of the laws of nature that has a specific value, but whose value is not derived from any deeper principle. It appears in Maxwell's equations as the speed of propagation of electromagnetic waves. It appears in special relativity as the universal speed limit, the maximum speed at which any causal influence can propagate. It appears in the famous equation E equals mc squared as the conversion factor between mass and energy. It is, in every meaningful sense, the most important number in physics, and we have no explanation for why it is what it is. What we can do is ask what would happen if it were different. What if the speed of light were 10 times faster, 1,000 times slower? What would change, and more importantly, what would break? The answers are more specific and more alarming than most people expect. Changing the speed of light does not merely make some things faster or slower. It changes the structure of atoms. It changes the stability of matter. It changes whether chemistry is possible. It changes whether stars can form and burn. It changes whether the universe can contain anything recognizable as structure. The speed of light is not a speed in the ordinary sense. It is a parameter that sets the scale of all electromagnetic interactions. And electromagnetic interactions are what hold matter together, what allow chemistry, what allow biology, what allow you to exist. This video goes through what the speed of light actually is, why it has the value it does from a theoretical perspective, what the consequences are of changing it, and what the fine-tuning of this constant implies about the nature of the universe we inhabit. There is a specific calculation in the fourth section of this video that produces the most striking consequence of changing the speed of light. Not the obvious consequences, but a consequence involving the stability of atomic nuclei that most people who have thought about this problem have not considered. Stay with me. Before we continue, the speed of light is not just a speed. It is the conversion factor between space and time in special relativity. It is the ratio between electric and magnetic field strengths in electromagnetic waves. It is the parameter that determines how tightly electrons are bound to atomic nuclei. Drop a comment with what you think would be the first thing to break if the speed of light were changed. We will come back to whether you were right. To understand why the speed of light is what it is, you first need to understand what the speed of light actually is, which is different from what most people think. The speed of light is not primarily the speed of photons. That is the consequence, not the definition. The speed of light is the speed of causality, the maximum speed at which any causal influence can propagate through space. In special relativity, the structure of spacetime is determined by a single parameter, the speed at which the light cone, the boundary between regions of spacetime that can and cannot causally influence each other, opens. This speed is c, the speed of light. Everything inside the light cone of an event can be causally connected to it. Everything outside cannot. The speed c is not a property of photons. Photons travel at speed c because they are massless. Any massless particle, in a universe with Einsteinian spacetime structure, travels at exactly c. If you discovered a new massless particle tomorrow, it would also travel at c. The speed of light is the speed at which massless things travel, not a property of the specific massless things we happen to know about. The appearance of C in Maxwell's equations, the equations that describe electromagnetic fields and their propagation, is therefore not a coincidence. Maxwell's equations describe the propagation of a disturbance in the electromagnetic field. The electromagnetic field is a physical field that exists in space-time. The speed at which disturbances in any field propagate is determined by the properties of that field and of the space-time it exists in. For the electromagnetic field, the propagation speed is determined by two constants: the electric permittivity of free space, epsilon 0, and the magnetic permeability of free space, mu 0. Maxwell showed in 1865 that the speed of electromagnetic waves is 1 divided by the square root of epsilon 0 times mu 0. When he calculated this from the measured values of these constants, the result was 310,740,000 meters per second, close to the measured speed of light at the time. Maxwell immediately recognized that light was an electromagnetic wave. The appearance of C in E equals the fine structure constant offers a partial way around the question of why C has its specific value. The fine structure constant, designated alpha, is a dimensionless number approximately equal to 1 over 137. It characterizes the strength of the electromagnetic interaction. It appears in calculations of how electrons interact with photons, how atoms absorb and emit radiation, how chemical bonds form. Alpha is defined as E squared divided by 4 pi epsilon 0 h bar c, where E is the electron charge, h bar is the reduced Planck constant, and c is the speed of light. It combines 4 fundamental constants of nature into a single dimensionless number. The significance of alpha being dimensionless is that it is the same in any system of units. The speed of light, measured in meters per second, depends on the definition of the meter and the second, both of which are human conventions. Alpha does not depend on any human convention. It is a pure number, the same for any observer in any unit system. When physicists ask whether the speed of light could be different, what they really mean, in a physically meaningful sense, is whether alpha could be different. A universe with a different speed of light but the same alpha would be physically identical to ours, just with different unit conventions. A universe with a different alpha would be genuinely different. Alpha is what matters, and alpha is approximately 1 over 137. Nobody knows why. Richard Feynman described the mystery of alpha as one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. That was in 1985. The mystery has not been resolved. Now, let's follow the consequences of changing the speed of light, or more precisely, of changing the fine structure constant alpha, through physics, chemistry, and biology. The starting point is atomic structure. The size of an atom is determined by the balance between the electromagnetic attraction of the nucleus and the quantum mechanical behavior of electrons. Electrons cannot collapse into the nucleus because quantum mechanics, specifically the Heisenberg uncertainty principle, prevents them from being both precisely localized and precisely at rest. The electron occupies a region of space, the atomic orbital, that represents the compromise between electromagnetic attraction pulling it toward the nucleus and quantum pressure pushing it away. The size of this region, the Bohr radius, the characteristic size of a hydrogen atom, is determined by the fine structure constant alpha, Planck's constant, and the masses of the electron and proton. Specifically, the Bohr radius is proportional to 1 divided by alpha. If alpha were larger, if the electromagnetic interaction were stronger, the Bohr radius would be smaller, atoms would be smaller, the orbitals in which electrons live would be more compact. The entire structure of atomic physics would be compressed. If alpha were smaller, if the electromagnetic interaction were weaker, the Bohr radius would be larger, atoms would be bigger, electrons would be more loosely bound to their nuclei. This has immediate consequences for chemistry. Chemical bonds, the connections between atoms that form molecules, are electromagnetic phenomena. They involve the sharing or transfer of electrons between atoms, governed by the electromagnetic interaction. The strength of chemical bonds, the energy required to break them, scales with alpha. If alpha were larger, chemical bonds would be stronger. Molecules would be more difficult to break apart. Chemical reactions, which involve the breaking and forming of bonds, would require more energy. The entire energy scale of chemistry would shift upward. If alpha were smaller, chemical bonds would be weaker. Molecules would be more easily disrupted. Chemical reactions would require less energy. At some critical value of alpha, chemical bonds become too weak to maintain stable molecules at the temperatures produced by stars, and chemistry, as we know it, ceases to be possible. The specific value of alpha, approximately 1 over 137, places us in a regime where chemical bonds are strong enough to maintain stable molecules, but weak enough to allow chemistry to occur at biologically relevant temperatures. Slightly larger, and life would require temperatures so low that liquid water is unlikely. Slightly smaller, and molecules are too fragile to maintain the structural integrity required for biological function. This is not a precise statement. The relationship between alpha and biological possibility is not a sharp threshold, but the general direction is clear. The observed value of alpha is in a range compatible with chemistry and biology. Values significantly different would not be. The fine structure constant alpha equals e squared over 4 pi epsilon naught h bar c is approximately 1/137.036, was named by Arnold Sommerfeld in 1916, who introduced it in the context of relativistic corrections to the Bohr model of the hydrogen atom. Its appearance in atomic spectra, specifically the ratio of the splitting of spectral lines to their central frequency, gives it its name. The Bohr radius, A0 equals h bar over alpha times me times c, approximately equals 5.29 times 10 to the minus 11 meters, sets the characteristic length scale of atomic physics. All atomic lengths are proportional to the Bohr radius, and therefore inversely proportional to alpha, making alpha the single most important dimensionless parameter in atomic and molecular physics. The consequences for atomic structure are significant. The consequences for nuclear physics are more severe. Atomic nuclei are held together by the strong nuclear force, a force that is much stronger than electromagnetism at nuclear distances, but falls off rapidly with distance. The stability of a nucleus depends on the balance between the strong force, which holds protons and neutrons together, and the electromagnetic repulsion between protons, which pushes them apart. The electromagnetic repulsion between protons inside a nucleus scales with alpha. Larger alpha means stronger electromagnetic repulsion between protons in the nucleus. At some value of alpha, larger than the current value, the electromagnetic repulsion exceeds the strong force's ability to hold the nucleus together. At that point, nuclei are unstable. Not just heavy nuclei, which are already marginally stable due to the growing dominance of electromagnetic repulsion in large nuclei. All nuclei above a certain size become unstable. The calculation is approximate. It depends on the specific model of nuclear structure used, but the general result is that increasing alpha by a factor of approximately 2 to 3 would make nuclei heavier than hydrogen unstable. The electromagnetic repulsion between protons would exceed the strong force's binding capacity for any nucleus containing more than a few protons. In a universe where only hydrogen is stable, where helium, carbon, oxygen, and every heavier element is radioactive and decays rapidly, the periodic table effectively ends at element 1. No carbon, no oxygen, no nitrogen, no phosphorus, no calcium, no iron. No carbon means no organic chemistry. No organic chemistry means no biochemistry. No biochemistry means no life as we know it. The constraint on alpha from nuclear stability is more stringent than the constraint from chemistry. You could imagine a form of chemistry using only hydrogen compounds, hydrogen bonds to hydrogen in various configurations. But the chemistry of hydrogen alone is extraordinarily limited. It does not produce the structural diversity or the information storage capacity that biology requires. Going in the other direction, reducing alpha significantly, also creates problems, though different ones. If alpha were very small, if the electromagnetic interaction were very weak, electrons would be very loosely bound to nuclei. The Bohr radius would be very large. Atoms would be enormous. The energy scales of chemistry would be very low. But the energy scales of nuclear reactions would also change. The rate of nuclear fusion in stars depends on the electromagnetic repulsion that must be overcome for two nuclei to get close enough for the strong force to take over. Weaker electromagnetic repulsion, smaller alpha, means fusion occurs more easily, at lower temperatures and pressures. In a universe with a much smaller alpha, stars would burn much faster. The fusion reactions that power stars against gravitational collapse would proceed at higher rates. Stars of solar mass would exhaust their fuel in millions rather than billions of years. The Sun has been burning for 4.6 billion years and has approximately 5 billion years remaining, a total main sequence lifetime of approximately 10 billion years. This is long enough for complex life to evolve, given the geological record on Earth. If the Sun burned for millions of years instead of billions, the development of complex life would be far less likely. The timescale is simply too short for the evolutionary processes that produced intelligent observers. The fine structure constant sits in a range that allows both nuclear stability for elements heavier than hydrogen and stellar lifetimes long enough for complex life. The range is not infinitely narrow, there is some slack, but it is narrow in the sense that values significantly larger or significantly smaller produce universes that are observably and importantly different. The constraint on alpha from nuclear stability was analyzed by Freeman Dyson in his 1979 Reviews of Modern Physics paper, Time Without End, Physics and Biology in an Open Universe, and developed in detail by John Barrow and Frank Tipler in their 1986 book, The Anthropic Cosmological Principle. The specific threshold value of alpha, above which multiproton nuclei become unstable, depends on the model of nuclear structure. Estimates range from approximately 2 to 10 times the current value. The constraint from stellar lifetimes was analyzed by Brandon Carter in his 1974 paper introducing the anthropic principle in its modern form. Stop here. Increasing alpha by a factor of 2 to 3 would make every nucleus heavier than hydrogen unstable. The periodic table would end at element 1. No carbon, no oxygen, no nitrogen, no organic chemistry at all. A universe of hydrogen gas. If you were designing the physical constants of a universe specifically to allow for maximum chemical complexity, maximum possibility for life, what value would you choose for alpha? Drop your estimate below. The answer turns out to be remarkably close to 1 over 137. The constraints we have just described, from chemistry, from nuclear stability, from stellar lifetimes, define a range of values of alpha that are compatible with the existence of complex chemistry and life. The current value of alpha, approximately 1 over 137, sits within this range. The question is whether this is a coincidence, a consequence of some deeper principle, or an anthropic selection effect. Let's start with what we know. The value of alpha has been measured with extraordinary precision. The most precise measurement comes from the anomalous magnetic moment of the electron, the slight deviation of the electron's magnetic moment from the value predicted by the Dirac equation. The measurement, by Gabriels and colleagues at Harvard, gives alpha to 12 significant figures. 1 over 137 0.035999084, with an uncertainty in the last digit. 12 significant figures. The most precisely measured physical constant in the history of science. We know the value of alpha to 12 decimal places. We have no theory that explains why it has this value rather than any other. The standard model of particle physics does not predict alpha. It treats alpha as an input, a parameter that must be measured and inserted into the theory, not derived from it. The standard model is the most precisely tested physical theory ever constructed. It predicts the anomalous magnetic moment of the electron to 12 decimal places, in agreement with the measurement. But it does not explain why the input value of alpha is what it is. String theory, the leading candidate for a theory beyond the standard model, in principle could predict alpha from more fundamental parameters. In practice, string theory produces a landscape of possible vacuum states, each with different values of the physical constants including alpha. The landscape contains an enormous number of possible values. Estimates suggest 10 to the 500 or more. Without a selection principle that picks out one value from the landscape, string theory explains why alpha has some value, but not why it has the specific value it has. The Anthropic selection principle, the observation that observers can only exist in universes where the constants take values compatible with the existence of observers, provides a possible explanation. In a multiverse where different regions have different values of alpha, observers find themselves in regions where alpha is compatible with complex chemistry and long-lived stars, because those are the only regions where observers can exist. This is the anthropic argument for alpha. And like the anthropic argument for the cosmological constant, which we discussed in the dark energy video, it is unsatisfying as a physical explanation while being difficult to dismiss as a logical argument. There is an alternative possibility that is taken seriously in some research programs. The values of the physical constants are not arbitrary. They are related to each other through constraints that a complete unified theory would derive. The current value of alpha is not arbitrary. It is the value that a complete theory of quantum gravity and particle physics would predict, given the other constants of nature. This possibility cannot currently be tested. We do not have the complete unified theory. But it motivates the search for such a theory, the hope that the apparent fine-tuning of physical constants is an illusion produced by the incompleteness of current physics, and that a deeper theory will make the observed values seem natural. Paul Dirac noticed in 1937 that several apparently unrelated ratios of fundamental constants, the ratio of the electromagnetic force to the gravitational force between a proton and an electron, the ratio of the age of the universe to the time for light to cross a proton, were all roughly equal to 10 to the 40th. He called this the large number coincidence, and speculated that it was not a coincidence, that there was a deep relationship between microscopic and cosmological physics that made these ratios similar. Dirac's large numbers hypothesis was not confirmed. The coincidences he identified may be approximate and transient rather than fundamental, but the impulse behind it, the sense that the numerical values of the physical constants are not arbitrary, that they are telling us something about a deeper structure, remains a motivation for theoretical physics. We have measured alpha to 12 decimal places. We do not know why it is 1/137th rather than 1/100th or 1/200th or 1/10th. We know what would break if it were different. We do not know what determined it. The most precise measurement of the fine structure constant is derived from the anomalous magnetic moment of the electron, G-2. The 2023 measurement by Fan, Myers, and Gabriels at Harvard using a single electron in a penning trap gives alpha to the power of -1 equals 137.0359999166, plus or minus 0.00000015, achieving a precision of 0.11 parts per billion. This measurement agrees with the theoretical prediction of quantum electrodynamics to 12 significant figures, the most precise agreement between theory and experiment in the history of science. Richard Feynman described the level of agreement as equivalent to measuring the distance from Los Angeles to New York to the accuracy of the width of a human hair. Alpha is not the only physical constant that appears fine-tuned for the existence of complex life. It is one of several, and the constraints from multiple constants operating simultaneously are more stringent than any single constant considered in isolation. The gravitational constant g, which determines the strength of gravity, is the weakest of the four fundamental forces by an enormous margin. The ratio of the electromagnetic force to the gravitational force between a proton and an electron is approximately 10 to the 36th. Gravity is 36 orders of magnitude weaker than electromagnetism. This weakness of gravity is not understood. It is called the hierarchy problem. Why is gravity so much weaker than the other forces? Various theoretical frameworks, supersymmetry, extra dimensions, the Randall-Sundrum model, have proposed explanations, but none has been confirmed. But the weakness of gravity is also necessary for the existence of complex structures. If gravity were stronger, if g were larger, stars would be more massive, would burn faster, would exhaust their fuel before complex life could evolve. Planets would be more massive, with stronger surface gravity, possibly exceeding the structural limits of biological materials. If gravity were weaker, if g were smaller, stars might not form at all. The collapse of gas clouds into stars requires gravity to overcome the thermal pressure of the gas. Sufficiently weak gravity would leave the universe as a diffuse gas, never condensing into the structures, stars, galaxies, planets, that provide the energy sources and stable environments for chemistry and life. The ratio of the strong nuclear force to electromagnetism, approximately 137 times alpha, roughly 1, is also constrained. If the strong force were slightly weaker, protons and neutrons would not bind to form stable nuclei. If it were slightly stronger, all hydrogen in the early universe would have been converted to helium-2, a form of helium that does not exist in our universe because the strong force is just barely too weak to make it stable. Without hydrogen, the chemistry of water, which requires hydrogen, would be impossible. The carbon resonance level, the specific energy level in carbon-12 that allows the triple alpha process to proceed efficiently, producing carbon in stellar interiors, is another example. Fred Hoyle predicted this resonance level in 1953 before it was experimentally confirmed, precisely because its existence was necessary to explain the observed abundance of carbon in the universe. The resonance level is positioned with an accuracy of a few percent relative to where it needs to be for efficient carbon production. Hoyle called the coincidence, the positioning of the resonance level, evidence for a super intellect having monkeyed with physics. He was not a theist. He was expressing his sense that the coincidence was too precise to be accidental. The ensemble of these constraints, alpha, g, the strong force coupling, the carbon resonance, forms what physicists call the fine-tuning problem. The observed values of the physical constants are not arbitrary. They are constrained by the requirement that complex structures, atoms, molecules, stars, planets, life, can exist. The constraints are not infinitely tight. There is a range of values for each constant that would permit some form of chemistry and some form of long-lived energy sources. But the range is not infinite, and the observed values are within it. Why? Three possibilities: coincidence, deep theory, anthropic selection. None has been established as correct. All three are taken seriously by working physicists. The speed of light, or more precisely alpha, which is the dimensionless combination of c with other constants, is one parameter in this ensemble. Its value is known to 12 decimal places. Its explanation is unknown to all decimal places. Fred Hoyle's 1953 prediction of the 7.65 megavolt resonance state in carbon-12, the Hoyle state, is one of the most celebrated examples of the anthropic principle being used as a predictive tool before the term was coined. Hoyle reasoned that since carbon exists in the universe in the observed abundances, the triple alpha process that produces it in stellar cores must be efficient, which requires a resonance state at approximately the right energy. The resonance was confirmed experimentally by Fowler, Dunbar, Pixley, and Wenzel at Caltech in 1953. Hoyle's famous statement about a superintellect was made in 1981 and is frequently quoted in discussions of fine-tuning, though Hoyle himself did not interpret it theistically. There is a question about alpha that adds an additional layer to the discussion. Is alpha truly constant, the same everywhere in the universe and at all times throughout cosmic history? The Standard Model assumes it is. Fundamental constants are called constants because they are assumed not to vary, but this assumption can be tested. In 2001, John Webb and colleagues at the University of New South Wales published a paper in Physical Review Letters, reporting evidence that alpha was slightly smaller in the distant past, at high redshift, corresponding to the early universe, than it is today. The evidence came from the analysis of absorption lines in the spectra of distant quasars. The absorption lines are produced by gas clouds between the quasar and Earth. The gas absorbs specific wavelengths of light, and those wavelengths depend on the atomic energy levels, which depend on alpha. If alpha were different in the early universe, the absorption line wavelengths would be shifted in a specific pattern relative to the laboratory values. Webb and colleagues reported a shift consistent with alpha being approximately 1 part in 100,000 smaller at redshifts of 0.5 to 3.5, corresponding to cosmic epochs between 4 and 10 billion years ago. The result was controversial. Independent groups analyzed different quasar samples and found no evidence for variation. Some analyses found a spatial variation, alpha being different in different directions on the sky, suggesting a possible systematic error in the original analysis rather than a genuine temporal variation. The current status is that the Webb result has not been confirmed by independent analyses at comparable precision. Most physicists consider it likely to be a systematic effect rather than a genuine variation in alpha. But the analysis has not been definitively closed, and the question of whether alpha could vary, even at levels far below current measurement precision, remains theoretically open. A varying alpha would have profound implications. If alpha changes over time, then the physical constants are not truly constant. They are dynamical variables, fields that evolve. The physics of the early universe would be different from today's physics in a way that affects every atomic process that occurred then. It would also open a door to understanding why alpha has its current value. If alpha is a dynamical variable, if it evolves according to some equation of motion, then its current value might be the result of that evolution from some initial condition, rather than a fixed parameter of the laws of physics. Currently, alpha appears to be constant to extraordinary precision. The quasar absorption line measurements constrain any temporal variation to less than a few parts per million over the last 10 billion years. Atomic clock comparisons, comparing different types of atomic clocks whose rates depend on different powers of alpha, constrain current variation to less than 10 to the negative 17 per year. Constant, as far as we can measure. Why constant? We do not know. Why this value? We do not know. 12 significant figures of precision, 0 significant figures of explanation. The speed of light is 299,792,458 meters per second. It is the speed of causality, the maximum speed at which any influence can propagate through space. It is the conversion factor between space and time. It is the parameter that determines the scale of all electromagnetic interactions through the fine structure constant alpha. Alpha is approximately 1 over 137. It has been measured to 12 significant figures. It determines the size of atoms, the strength of chemical bonds, the stability of atomic nuclei, and the lifetimes of stars. Values of alpha significantly larger would make multi-proton nuclei unstable. The periodic table would end at hydrogen. No carbon, no organic chemistry, no biology. Values of alpha significantly smaller would weaken chemical bonds below the threshold for stable molecules at biologically relevant temperatures. Stars would burn faster, exhaust their fuel before complex life could evolve. The observed value sits in the range compatible with complex chemistry, nuclear stability, and long-lived stars. We have no explanation for why it has this value. The Standard Model treats it as a measured input. String theory produces a landscape of possible values without selecting among them. The Anthropic argument explains why observers find themselves in a universe with a compatible value without explaining what determines the value in any given region of the multiverse. Richard Feynman described alpha as one of the greatest damn mysteries of physics. That was 1985. The mystery has not been resolved. The number is 1 over 137. It is precise to 12 decimal places. It has no explanation. It is the number the universe chose, for reasons we do not understand, that makes you possible. One question. The fine structure constant alpha, the dimensionless combination of the speed of light, the electron charge, and Planck's constant, is approximately 1 over 137. Richard Feynman described this as one of the greatest unsolved mysteries in physics. If you could choose the value of alpha for a new universe, what would you choose and why? Not to maximize complexity or life. What value feels right to you, and what would you sacrifice to get it? Drop your answer below. Next video. When two galaxies collide, what actually happens when the Milky Way and Andromeda merge in 4.5 billion years? Why most stars pass through each other without colliding? What happens to the two central supermassive black holes? And what the solar system's orbit looks like during and after the merger. See you there.